All right, today we're going to talk about I can generate function tables from function rules and use the sets of ordered pairs to graph the functions. So let's look and see what a function table is. So a function table organizes the input and the output of a function. So in 5-1, we did talk about an input and an output. An input is our x value. Our output is our y value. And a function table is going to then allow us to talk about this function where we input our x value and we're going to come out with a y value. You can create a function table from a function rule by substituting appropriate input values into the rule, then simplifying to find the output. So what they mean by that is, for instance, we're going to take our input. So say our input is 1. We're going to plug it in for our x. We're going to say 2 times 1 is 2 plus 3 is 5, so we get a 5 as our output. Okay, so we take our input, plug it in. When we add that together, we're going to get an output. And we're going to keep doing that so that we can come up with our ordered pairs. So when we look at this, the idea is we're going to end up with our x, y ordered pairs. So we're going to have 1, 5. We're going to have 2, 7, 3, 9, and 4, 11. Okay, so it's this idea that we can come up with those ordered pairs, and then once we get those, we can graph them. So let's look at this first one. So the idea is we're going to have our -2. We're going to plug that -2 in for the x. So all of these are our x values that we have for our input, and we're going to get our y values out. So you probably are going to have to do some work on the side. So say if we had 4 times -2 minus 1, that means we're going to get -8 minus 1, which gives us a -9. Okay, again, we're going to have 4 times 0 minus 1, so that means we're going to have 0 minus 1, which means we're going to have 0. So you're probably going to have to do, oops, not 0, -1. So you'll probably have to do some work on the side. You're not just going to be able to write your output values out. So go ahead and try this check function. Now that you've tried the check function, this is what you should get. Notice how they didn't include the equation. So for your table, I really want you to have your input, your function, your output, and I even want you to have your ordered pair, okay? So what that means is you're going to have your x value, your function. So for us, this is y equals -4x minus 3. Your output, which is your y value, and then your ordered pair, which is your x, y. So for our table, what we're going to end up with is we're going to have a -1, 1, 3, 5, which is the numbers that they list for us. So we're going to go ahead and draw our table. So that tells us we're going to have our -4 times -1 minus 3, -4 times whatever the x value is minus 3, and we're going to keep doing that down this whole table. But instead of an empty parenthesis or an x, we're going to plug in the value that we're given. So next we have 1, then we have 3, next we have 5. Then we're going to actually have to solve the equation. So we have -4 times a -1 is a +4, minus 3 gives us a +1. So my coordinate point is a -1, 1. Next, we're going to have -4 times a +1, which is a -4. Minus 3 gives us a -7. So our next point is going to be a 1, -7. Don't forget your parentheses. And next, of course, -4 times 3 gives us a -12. Minus 3 gives us a -15. So another point on our graph is going to be 3, -15. And then we're going to have -4 times 5, which is a -20. Minus 3 gives us a -23. So our final point is going to be 5, -23. Next. So let's look at example number 2, it takes approximately 770 peanuts to produce 1 jar of peanut butter. The total number of peanuts, N. Okay, so we have our total number of peanuts, which is N, is represented by this function right here. We have N equals 770p. So don't forget, 770 is our peanuts to produce 1 jar of peanut butter. And then our total number of peanuts we're going to end up using is our value N. So P stands for our what? What does P stand for? N is our total number of peanuts, so P must stand for our jar of peanuts. Okay, so it doesn't tell us that, but oh yes it does, right here. P is the number of jars of peanut butter. Don't forget to read the whole problem. So determine appropriate input values for this situation when then complete a function table for this function n equals 770p. Determine an appropriate input values for this situation. So the idea is we're definitely only going to be able to use whole numbers. So part A, determine the appropriate values. Only whole numbers make sense for the input because you cannot buy a fraction of a jar. So remember how before we were talking about like a dotted line? So because we can only have whole numbers, this means that we're going to have a dotted line because we can't have half of a jar, right? We can't have half of a jar, we can't have negative jars, so they have to be whole numbers. So we're going to use 1, 2, 3, and 4. So our output, so the idea is if we were to use the function of n equals 770p, the idea is that we would have had 770 times 1 to get our 770. Next, we would have done 770 times 2 to get our 1,540. And then we're going to keep going with 770 times 3 to give us our 2,310. And lastly, 770 times 4 to give us our 3,080. So let's go ahead and work on this check. It is a multiple choice. So an online photo printing service charges 15 cents per photo and $2.99 for shipping. So because I see the word per, this is going to be my slope. So if we were to look at it like y equals mx plus b, notice how the coefficient is our 0.15, and then we have to pay a flat fee of $2.99 or a initial cost of $2.99 for shipping. So we are still working on slope-intercept form, except for they're kind of going to already give us those equations. So C stands for our total cost of printing and shipping any number of pictures, P. So our total cost is C, and a number of pictures is our P, or our P value. And then they give us our function C equals 0.15p times 2.99, right? And then it says what input values of P make sense. So if we're talking about number of pictures, again, we're going to run into that situation where it's going to have to be whole numbers. We're going to have a dotted line. That's the other idea I need you to pull from this. So we're going to complete our table. When we complete our table, what I would suggest doing is writing down your function with parentheses where we're going to plug in our input value, which is P. So go ahead and write the equation down 4 times because that's how many numbers in our table we have. So we get C equals 0.15 parentheses plus 2.99. C equals 0.15 parentheses plus $2.99. Then we're going to plug in our values. We have 1, 2, 3, and 4. So remember, those have to be whole numbers. We're going to plug that into our calculator, and then that's when we should get our 3.14, 3.29, 3.44, and our 3.59. Moving on. Next, let's talk about graphing. So the graph of the function is the set of ordered pairs right? Our ordered pairs are x, y, our coordinate points, consisting of an input with the corresponding output that make the equation representing the function true. A linear function is a function in which the graph of the solution forms a straight line. We've talked about this before. Therefore, an equation in the form of y equals mx, so remember this is directly proportional, goes through the origin, 0, 0, or we have our y equals mx plus b, where m is our slope and b is our y-intercept. And we call this slope-intercept form, right? Those are the two equations we're going to be using. They're basically the same thing. So a function y equals x minus 1 is represented by a table ordered pairs and graph below. So when we look at this, if we were to take 0 and plug it into our equation, 0 minus 1 does give us a negative 1. If we were to write that as an ordered pair, we'd have 0, negative 1. If we were to look at our graph, we start at 0, 0, the origin, and we notice our first point is at 0, negative 1. Next, we're going to get 1, 0, and then that's going to be this point right here. We have 1, 0, and we're just going to keep plotting our points from our graph. So let's look at this first example. So we're going to create a function table for the function y equals x plus 2, then graph it. So select values for the input x, such as 0, 1, 2, 3. So the idea is usually we want to start with 0. Sometimes we want to start with a negative number, and then we're going to get our points. So notice how we have our input, then we have our function, then we get our output, then we have our ordered pairs. So now if we plug it in, you should write down that we get out a 2. And so our ordered pair is going to be 0, 2. Next, 1 plus 2 gives us 3. So our ordered pair is 1, 3, and so forth. We're going to have 4, and then 5. Because each time we are adding 2. Next, let's graph that. So we're going to graph our first point, which is going to be 0, 2. Then you're going to graph the next point, which is going to be 1, 3, and so forth. Do not forget your arrows. And in this situation, we're going to have it going off into infinity in both directions. All right, so go ahead and try this check. Pause the video. Now that you've tried the check, we're going to create a function table for the function y equals negative 3x plus 4. So you should have written down x. We should have had the equation negative 3 times x plus 4. We have our output y, and then you should have your ordered pairs x, y. So even though they don't give that to us directly, we need to understand that we're going to have our input x, our function, our output y, and then our ordered pair x, y. So like I said, sometimes you want to start with a negative number. So we had negative 1, 0, 1, 2. You should then plug that in. So we're going to have negative 3 times negative 1 plus 4. Then we're going to have negative 3 times 0 plus 4. Notice how I'm just inputting my x value into those parentheses. That's why I want you to write parentheses when you are writing your function. So we have negative 3 times negative 1 is a positive 3 plus 4. That's how they got 7. So our first order pair is negative 1, 7. Next, we have 3 times 0, which is 0, plus 4 is 4. So we're going to have 0, 4. And we should have that. That's our y-intercept. So that's our y-intercept. That's this guy right here. Then we're going to have negative 3 times 1, which is negative 3 plus 4 is a positive 1. So our next point is going to be at 1, 1. And lastly, we're going to get negative 6 plus 4 gives me a negative 2. So we're going to have a point at 2, negative 2. So there's our points. you should have plotted those on the graph. So notice how we have our y-intercept at 0, 4. Then you should plot a point at 1, 1. You should also have a point at negative 1, 7. And a point at 2, negative 2. Now let's go to the next. We're going to look at the apply problem. So we have a taxi service that charges $2.50 plus 75 cents per mile. The function, so they do give us our function, our slope-intercept, represents the total cost in y. So that's what our y values represent. And then our number of miles is our x. If Adrian rode 10 miles, so since x equals our miles, we know x equals 10, and Alonzo rode 15, so Adriana is our 10, and then Alonzo is when x equals 15. We're asked how much more did Alonzo spend on his taxi ride. So we have to plug our x values into our equation and then compare our total costs. So what that means is we're going to end up saying, okay, we have Adriana, I'm just going to do AD, and then Alonzo, AL. Adriana is when we have x equals 10. Alonzo is when x equals 15. We're going to be using y equals 0.75x, but instead of an x, I'm going to put parentheses plus 2.5. And then we're going to have Alonzo, and so we're going to plug in his x value. So we're going to still rewrite the same equation, but we're going to end up putting two different numbers in, and we're going to compare our total costs wise. So we're going to plug in 10 miles for Adriana. We're going to plug in 15 for Alonzo, and we're going to compare their costs. So we could already probably make a guess and say, well, we already know Alonzo is going further, so he's going to have to pay more, but we're asked how much more. So we're going to plug this into our handy dandy calculator. We're going to get, let's see, $7.50 plus $2.50. So he's going to have to pay she's going to have to pay a total of, let's see, $7, $8, $9, $10. Then we have Alonzo, and Miss Campbell is definitely going to have to use a calculator for this. If you have to use a calculator for the other part, that is perfectly fine. So we have 75 cents times 15. We get $11.25 plus $2.50. And so the total cost for Alonzo is going to end up being $13.75. And so when we look at the difference, if we do 13.75 minus 10, what we're going to end up with is $3.75. So Alonzo's going to have to pay $3.75 more. Alonzo pays $3.75. Okay. So now what I want you to do is try this on your own. Pause the video. All right, now that you've tried it, an elephant weighs 200 pounds at birth and gains approximately 2 pounds per day. They do give us our function. So our starting is 200 pounds, and then we're adding 2 pounds per day. And this represents the weight W of an elephant. So the weight is the W of an elephant during any given day. So a day is the D during his first year. How much more does an elephant weigh on day 60 versus day 5? So we're going to say when our day equals 60, we're comparing that to when our day equals 5. So we're going to have our equation, W equals 2 times 5 plus 200. And we're going to compare that to when we have our weight equal 2 times 60, because that's our day, 60 days plus 200. So for this one, we're going to have 10 plus 200. So it's going to be 210 for the weight. And weight is, they don't tell us, oh, it is in pounds. So After 5 days, it's going to be 210 pounds. After 60 days, we're going to have 120 plus 200. So that tells us we're going to have 320 pounds. And so that means we're going to take 320 minus our 210, and we're going to end up with 110 pounds more, because that's how much more pounds the elephant weighed after from 5 days to 60 days. Go ahead and work on the homework. Let me know if you have any questions.